Chemical kinetics is an especially important part of chemistry. It describes how fast chemical reactions occur, and this is in contrast to when we spend time talking about thermodynamics, we talk about the energetics of a reaction. But the energetics of a reaction does not imply the speed of the reaction. So with kinetics, we are going to talk about the rate of reaction. And when we fundamentally talk about this rate of reaction, we're just talking about the change in concentration, usually of a reactant, but also of products. Over a change in time. So if we think about an example reaction, let's think about the decomposition of dinitrogen pentoxide gas. And it can decompose into 2 nitric oxide gases plus half an O2. So really what's probably happening is that you have 2 of these reacting. But that's okay. We can go ahead and write this with the fraction as there. So if we think about the rate of reaction of this dinitrogen pentoxide, this is going to have a certain change in its concentration over a change in time, but our reaction rate we want to be positive. So since the concentration of the dinitrogen pentoxide, we would figure this change as N2O5 final minus initial as usual, and T final minus T initial for whatever time interval we're looking at. So since the final is always going to be less than the initial, we're going to just go ahead and put a negative sign out here to reflect the fact that the reactant is being used up, and we still will get a positive rate. And the standard units for the rate are going to be molar per second. And that naturally is going to come from the molarity up here and the time over here. You could have molar per minute or some other time period as well. And we might use some other concentration unit, but this is sort of a standard one. So if we track the decomposition of the dinitrogen pentoxide, that's one way of calculating the rate, but we could also track the appearance of the nitrogen dioxide. And with this 2 in front of the nitrogen dioxide, we can see that NO2 is produced twice as fast as the N2O5 is used. And similarly, since we have a 1/2 here, that O2 is produced half as fast as the dinitrogen pentoxide is used up. So the rate needs to be the same for all of these. So we can go ahead and relate these to each other by inverting the stoichiometric coefficient in here. So the rate of disappearance of the dinitrogen pentoxide is half as fast as the rate of appearance of the nitrogen dioxide, and it is twice as fast as the oxygen. Oop, I forgot my delta there. Okay, so this is one of the ways that we can talk about reaction rates, and it's if we track the reaction rate and then we graph it, then its shape is generally going to be downward if we're talking about the dinitrogen pentoxide over time. And if we're talking about the NO2, so it's generally downward, then it's generally going to be upward. So let's go ahead and look at an example graph. I'm going to pull up a graph of the decomposition of a dye. Okay, so this is the concentration of a dye over time. The dye is being oxidized by bleach or something like that, so that it gets used up. This is actually a typo as well. Let's switch back over. Okay. So when we look at this particular dye, I want you to note this is a typo. It actually should be 10 to the minus 5 molar. There's a typo in the book where I scanned this off of. So we're looking at the concentration changing over time, and we can use the equation that we just calculated to calculate the quantity of the dye, the rate of change over the dye. So let's calculate this rate over 2 intervals. We're going to take that first minute. We can see that the rate is changing though, so let's go ahead and calculate it over this minutes 5 to 6 as well. So pause the video and use the concept that we just developed to calculate the rate of reaction. Look at the changing concentrations. You may have to estimate what the concentrations of the dye are from this graph, and that's okay. Just do your best at estimating what those values are. Okay, so hopefully you were able to calculate that over this first minute, if we are estimating that this is about 3.4 times 10 to the minus 5 molar, and this is about 2.4 times 10 to the minus 5 molar, then we get a rate for this first minute of about 1 times 10 to the minus 5 molar per minute. And for this second time interval, we get a much smaller rate, which is 0.15, not equals yet, but 0.15 times 10 to the minus 5 molar per minute. And if you got slightly different numbers, that's okay. We just will get slightly different numbers because of the way that we are estimating these reaction rates. So since the rate is changing over time, it's not always convenient for us to just talk about the rate in terms of this changing amount of our reactant. And I'm actually going to switch over here to my differential terms here. If you haven't taken calculus, don't worry about it. This is effectively just the change in R over, or the change in the concentration of my reactant over the change in time. It's equivalent to what we just wrote. So rather than just talking about this rate, we are going to develop something called a rate law. And the rate law describes how each reactant or product, sometimes products affect the reaction rate, each reactant or product affects the reaction rate. And so the form of our rate law is going to be something like rate is equal to a rate constant that we'll talk about in a minute, and then we'll have reactant 1 taken to some exponent, reactant 2 taken to a different exponent, reactant 3, etc. for however many pieces you have that affect the rate of your reaction. So if the concentration of a chemical species that is participating in the reaction affects the reaction rate, then it will be included in the rate law. We have two methods of figuring out what our rates are like and what our rate laws are. So I'm going to review both of these. The first method that I'm going to talk about is called the method of initial rates. So in this method, we look at our chemical reaction. Let's say we have some nitric oxide gas that is reacting with oxygen in the atmosphere and combining to form some smog, or specifically nitrogen dioxide gas, which is the brown gas as part of smog. So in this reaction, it is possible that the nitric oxide and the oxygen both affect the reaction rate, but we don't know for sure. So we write a generic rate law that says rate is equal to the rate constant times my nitric oxide concentration taken to some exponent multiplied by the oxygen concentration taken to some other exponent. And the x and the y, these are called the order of the reaction. So if x is equal to 1 or y is equal to 1, this would be first order. If it's 2, that would be second order, 3, third order, and so on and so forth. Okay, so the way that we use the method of initial rates is that we're going to calculate the initial rate of reaction of these compounds for each other. So we're going to design an experiment where we change the concentrations intentionally, only changing one variable at a time, and then we measure the rate and see how it changes. So the way that your data will look is that you'll have several different experiments. So in this case, maybe we would have 3 experiments. We would have our nitric oxide concentration in molar units. We would have our oxygen concentration in molar units. And we would have our rate in molar per second or molar per minute, however the case was. So in order to keep our experiment under control, we're only going to change one variable at a time. So between, for example, experiment 1 and 2, we would keep the oxygen concentration the same, but double the nitric oxide concentration. And doubling is usually a good bet because it's easy to see the changes. If you do some strange fractions, then the math can become a lot harder. So mostly we do things like doubling. So these are some reaction rates. Excuse me, that's 5.0 times 10 to the minus 5. So in order to do the math for this, what we want to make use of is the fact that we have some numbers that are going to cancel out. So the reaction rate constant is the same. It's the rate constant, right? K is constant as long as we keep the temperature the same. Doesn't matter what else we do with the reaction. As long as we keep the temperature the same, that rate constant will be the same. So we take 2 experiments, and it's always good to put bigger numbers on the top unless you love fractions, which I don't. So I'm going to take the rate from the second experiment, the rate law. So this is going to be 1.0 times 10 to the minus 4. It's equal to a rate constant times my concentration of nitric oxide to some exponent x, and then 0.010 taken to the y, and I'm going to divide it by the experiment for 1. So the rates are dividing out each other. So my rate for experiment 1 is 2.5 times 10 to the minus 5, and my rest of my rate law will have the same concentration for the oxygen, but we changed the concentration for the nitric oxide. And this is also molar unit. Sorry, that got a little messy there, but we're about to cancel it out, so it will not matter. So notice here that these 2 numbers, whatever that exponent is, they're still the same number. So we can just cancel that out entirely. And then the k's cancel out. I was sloppy about the units here, but they're all going to cancel out anyway because we're just getting some ratio number. So you can see over here that this is 2 over 1 taken to the x power. And if I do this math, it will give me a 4. So these are made up numbers, which means that all the numbers are super tidy. You probably would end up needing to do some rounding off if you were taking some actual experimental data here. But we can pretty clearly see that x is going to be 2. So this reaction is second order. The rate law is second order in the nitric oxide. So we're going to do the same process for the other 2 experiments, where we will put experiment 3 on top and experiment 1 on top. And so if you go ahead and do that, I recommend that you pause the video and try it out. You should get that y is equal to 1 when you do that. So that means that our overall rate law is K times nitric oxide squared multiplied by oxygen. And please be really aware that these are all multiplied by each other. They are not added together. This is all multiplication. Okay. We have rate values that were in the experiment. We have figured out the order of the reaction. The only thing missing is for us to calculate the rate constant. So to calculate the rate constant, we can pick one of the experiments. Any of them would be fine. And we just plug in the numbers and solve for k, because that's our last unknown. So if you did 5 times 10 to the minus 5 is equal to k 0.01 squared 0.02 and solve for k, then you should get 25, unless I did it wrong. You should check my work. Anyway, because the reaction is third order overall, oh yeah, I wanted to clarify that, right? We have second order in nitric oxide, first order in O2, and the total order is the sum of those two orders. So second order plus first order is equal to third order overall. Third. Okay, now we're ready to move on. So I was about to say that we need to look at some units here, right? We know that even if I was being sloppy, this rate is in molar per second units. This concentration is in molar, it's squared, and this concentration is in molar also. And so the units for the K need to be able to cancel out all the extra stuff and get us to the same units on both sides. So in order to do that, we need a 1 over seconds to get the seconds over here, and then we need to get rid of 2 of those molar units. So the rate constant is going to have units that depend on the order. I'm going to write that down. Units of the rate constant depend on the order. So that's a quick reminder about how we do the method of initial rates. The second process that we might use, which probably is a little more common in experimental conditions, but it just depends on what your setup is for us to do integrated rate laws. So when we talk about integrated rate laws, we look at each order of rate law separately. Our process is the same for all of the integrated rate laws, but because each of the rate laws has a different result when we integrate it, we deal with it a little bit differently. So we'll start by talking about first order rate laws. And when we look at a first order rate law, we typically are just looking at one variable at a time. So we would just isolate all the information about, say, the nitric oxide. And we would analyze the data for the nitric oxide, decide on its order, and then move on to the next variable as appropriate. So for a first order reaction, we know that our rate was equal to the change in that reactant with time. And if I write that as a differential, then it looks almost the same. And that first order reaction would just have the R squared multiplied by the rate constant. So if you haven't done integral calculus, don't worry about it. You can just take my word for what the result is. But if we integrate this, then we would end up with natural log of the concentration of our reactant divided by that initial concentration, whatever it was, is equal to minus KT. So this is the same rate constant. T is time. And we need to remember that for natural logs, we have some special rules. If we have natural log of A over B, this is the same thing as natural log of A minus natural log of B. There's a whole bunch of trigonometric identities, and I'll mention them as they come up. So if we separate this out, natural log of r minus natural log of r sub I, initial, and then we think about how the reason why we're doing this is because we want to simplify our data. Remember, we had looked at the concentration of that dye, and we noticed that the rate change, it changed over time. And so it's not like it was super easy to describe what the rate was at any point. But if we rearrange this slightly, and now I'm actually going to move this part over to the other side, then we can realize that this looks like the equation of a straight line. So we can plot, instead of just plotting r directly, we can plot the natural log of the r versus time. It will have a negative slope, and so it will start and then it will decrease. And the b value, the intercept, will be the natural log of that initial concentration, so we can actually calculate that. And then the slope will be equal to minus the rate constant. And so this is super handy because we can go ahead and calculate the rate constant just by graphing data and looking at the slope. It also allows us to go backwards if we didn't know what the initial concentration was, like we weren't super careful about measuring that initial concentration, but we just measured the concentrations later on. We go back and find that as well. So the method of initial rates is a graphical approach to figuring out our rate law, because if we plot natural log of the concentration versus t and we have a linear plot, we also know that it's first order. One of the big picture pieces from integrated rate laws is that what we're trying to do is get a straight line relationship so that we can easily see so we can easily graph it and interpret the results. So that was the first order rate law, how we deal with that. Now we're going to go ahead and talk about second order. So the general form of our second order rate law is that reactant squared. And when we integrate it, we're going to get 1 over r minus 1 over the initial value of r is equal to kt. So again, if we look at how to graph this, if this is y and this is mx, we can move this over and it becomes b, and we have a nice line. So that means that we are going to be graphing 1 over the concentration versus the time. And if we do this time we have a positive k value, so that means our slope is going to be increasing, only it's linear, unlike exactly what I drew, but close enough. So the slope here is equal to just the rate constant. The intercept is 1 over the initial concentration of that reactant, and this gives us another straight line relationship. Now, the only other integrated rate law that we sometimes talk about is the zeroth order rate law, which sounds a little bit funny. But all it means is that the rate is constant, that if we think about the change in the concentration with respect to time, it doesn't depend on r at all. If you want to be super formal, then you can put the r in and put a 0 for the zeroth law. But remember that any value taken to the 0th power is just equal to 1. So this just cancels out. So in this case, we already have a graph of r versus t that is going to be linear. So we don't actually need to do anything to it. We can just graph r versus t, and the slope is going to be equal to minus k, and everything will be pretty straightforward. So b is equal to the initial value as usual. So these two methods, the integrated rate laws and the initial method of initial rates, are the two most common ways that when we look at reaction kinetics, we figure out what the order, what the dependence is of the concentration on the time. Now, all of this has been looking at concentration effects. Okay, there are other variables that can affect rate reaction too, and we'll talk about them later. Things like temperature. But concentration is one of the big ones that affects reaction rates, so we wanted to make sure to talk about this. The other small aspect that I wanted to cover here is half-life. Half-life gets talked about most often if we are talking about radioactive decay, but the concept of half-life is pretty straightforward. We usually use T sub 1/2 to simplify it, and the idea of this is that it's the time required for half of our reactant to be used up. So that means that our concentration of the reaction at time T 1/2, this is going to be 1/2 of whatever our initial reactant concentration was. So depending on what kind of rate dependence we have, so if we have a first order reaction, then we can look at our first order integrated rate law as an example of an easy way to deal with it. We know that this is the dependence, minus kT. And so if the concentration at time t at 1/2 is equal to half of the concentration, then we can plug those into this natural log. We will have 1/2 of R sub I over R sub I. So those guys are the same, they just cancel out. This is now natural log of 1/2. And here's another trigonometric identity that if we have natural log of A, it's equal to minus natural log of 1 over A. So if I have half, then this is the same thing as minus natural log of 2. And this way I can cancel out those two negative signs. So then my t, which is t 1/2, is equal to the natural log of 2, which is just a number, divided by the rate constant. And natural log of 2 is approximately 0.693 over k. All right. So remember how we talked about photolysis and how photolysis is a first order reaction? Well, radioactive decay is also a first order reaction, not radiation. So you can use this equation if you have the rate constant right here. We talked about the photolysis constant already. So if we have the rate constant, then we can just go ahead and calculate the lifetime. Now, in the photolysis lecture, we talked about the typical lifetimes, and that's different from the half-life, so just be clear about that. So you can calculate the half-life for second order and other order reactions as well. You just do what we did right here, where you plug in that our current concentration is equal to half of our initial concentration and then solve for the time. The other thing that you can do is if you want to find out, for example, what's the time at when we've used up 75% or 90% or whatever, just set that problem up exactly this same way where we instead put like R is equal to, well, if we used up 90%, then it would be only 1% of our initial. and then we can plug it into whatever our rate law is, our integrated rate law, and solve for t. So we'll have some example problems here in assignment number 8 that have to do with all of the pieces that we've just talked about. I'm going to go ahead and attach that to the Moodle separately.